Hello, my name is Patrick Yu, and
My name is Ethan Gordon.
we're here to talk to you about implementing CoinJoin. So first, what is CoinJoin? So what CoinJoin aims to solve is a lot of the problems surrounding traditional Bitcoin with issues regarding privacy. So mainly, what we're trying to do with CoinJoin is it's a protocol that's designed to build on top of Bitcoin and not replace Bitcoin, unlike some of the other privacy solutions you've heard about, like in ZeroCoin. So in Bitcoin, as you know, there's multiple inputs and then multiple outputs and possibly a change output for every single transaction. So what CoinJoin aims to do is it tries to implement a system where multiple users get together and then they basically participate in a single transaction, signing independently of each other, and receive the output, a set output that they decided upon earlier, a fixed size output of the Bitcoins that they put into the transaction. Essentially randomizing, kind of hiding their masking their output, so you can have your input and people wouldn't be able to know your output. And obviously this will be done in our implementation using Chom's blind signatures, so that the server doesn't actually know the mapping between the inputs and the outputs. So essentially this is the main idea behind CoinJoin.
Fun fact, CoinJoin.org actually is just a redirect to the forum post where it was proposed. So the difference about this project is that there actually are CoinJoin implementations in existence. The biggest one was actually created by Blockchain called SharedCoin. And it's also actually the only implementation that involves a GUI. The thing, though, is that these implementations don't quite match up to some principles that we learned in class from the Mixcoin paper, the 4 principles of mixing. So I'll just quickly run through those now. One is an automated client, and the only one that does this right now is SharedCoin. Basically, we made our CoinJoin implementation a plugin to the simple template Bitcoin wallet that is provided with the Bitcoin J source code. The second thing is a standard chunk size. And ShareCoin actually doesn't do this. Every single transaction on the entire server has the same output size. We set ours to 0.01 BTC. It's hard-coded right now. But every time the server starts up, every single transaction is going to have the same output size, so it becomes more difficult to distinguish between different transactions as well as within a transaction. Thirdly, it should be easy for these transactions to be chained together in rounds. This is also a problem with SharedCoin in that they put the responsibility of the transaction fee, which we'll also get into as the fourth thing, on the user. So the user has to put in a transaction fee for enough of a transaction fee to cover each round. But for ours, the output of each round can go directly as the input of the next round. And finally, transaction fees. They have to be all or nothing. And to make it easier, because we couldn't quite get ours to be both anonymous and have randomized transaction fees like a centralized mixer, we present Alice's altruistic mixer. Donations welcome. We basically put up an address, the server's address, so we can receive donations, and the server will apply the set transaction fee to each transaction, so that the user can just go round to round, just putting in their 0.01 BTC and not have a difference in Bitcoin with each transaction. A couple other goals. We want to make sure that our server can handle multiple transactions, so if a transaction is closed down and is getting ready for signatures, we have to be able to allow other people to then connect and create a new transaction just for scale. Secondly, all the API calls to the server happen on a separate connection, so the client will, on a different socket, disconnect after each API call and then reconnect for the next API call. This will allow the client to hide behind an anonymity network, so that the server knows nothing about who the client is. And finally, we have these nice colors in this image we are maliciously abusing, but the mixer will not know the mapping. And actually, SharedCoin doesn't do this either, because since blockchain, you send them both the final address and your account information so that they know the mapping of the entire thing. No one else does, but blockchain does. Our goal is to go further than that so that the mixer doesn't even know the mapping. So we're going to give a brief overview of our API. It's a very short one before we jump right into our demonstration. As Patrick mentioned, we do use Chom's blind signature and RSA in order to blind the output address. And each transaction has a different key pair, so that the RSA key can also be used to identify the transaction quickly. So the first API call just pulls the public key of the currently open transaction. Then the client can register their input by supplying a transaction output that they want to be redeemed by their input address, an optional change address, which will only be needed in the first round, the hash of the public key, which serves to identify the transaction, and the blind output address that's blinded and needs a signature. So the server will sign from that transaction's public key. Client disconnects and reconnects to register their output. They register their output address, and they send the signature of the output address. So the server can verify that this output address actually maps to the transaction they want to put it in, but doesn't know the mapping because it was blinded when they signed in the first place. So if all the users have sent their output address, then this API call will return the full transaction, and the user can disconnect again. When they reconnect the final time to register their signature, the user submits the signature and the index where the signature is supposed to go in the transaction. Once everybody has submitted their signature, the server broadcasts the transaction, and the client can always at any time check the status of a transaction just with this last API call. Alright, I think now we can do a demonstration. Oh wait. So our server, even though it runs on Bitcoin J, will automatically try to connect to any local Bitcoin D server or any local Bitcoin node that's running. So we'll start a Bitcoin D server and then start the server. Alright, some debugging code. So this address right here, can everybody see? This address right here is the donation address. That's blinking oddly. And we should have at least a Bitcoin in there right now. By the way, this is all in the testnet. We're not rich.
All the money there, right?
Yep. So it will then add a fee to all the transactions that need a fee. So now we'll start two clients. And this is actually the default wallet template. I'll move it down here. Start two clients. Each one with their own wallet, and each one looking very rich right now. So this is actually a full wallet. You can use it as a full wallet. You can receive money to this address, and you can always send money out. We just want to demonstrate how we can easily just plug this implementation right into a full wallet, albeit a simple wallet. So let's look at this one right here. The minimum chunk size is 0.01 BTC, so all the Bitcoin that you can mix will be listed on the left as every output that's at least 0.01 BTC. Actually, we'll do a big one so we can address. Here we can generate a new receive and a new change address, and then mix. It's not going to do anything yet because there's only one person. So it pulls the RSA key, blinds the output address, and then registers its input address, calling to the server. And then it unblinds the signature, but before sending the unblinded signature, it'll wait until the server says that the transaction's pending or it has all at least two inputs. A hard-coded value that we can certainly test and change. So we'll do the same thing with this guy over here, and just mix a small 0.01.
Right now the minimum number of participants is set at 2.
Yeah. Yep, so this is actually going to go kind of fast, so we can go back to the log. But now they're both pending. Then one was waiting for signing, now this one's waiting for broadcast, and now the transaction successful. And you can see we lost 0.01 Bitcoins there and gained it back on our output address, MJ's. And here, our 0.01 has moved to a new address, MUI 9. Yes. So that actually worked. It was broadcast to the entire testnet blockchain. just a brief look one more time at what was going on. After it was pending, it registered its output address, and it waited. The state moved to signing, which it did, and both received a signature. Signing transaction here, and signing transaction up here. So this, I forgot which one was waiting on broadcast. One of them was waiting for broadcast because the other one was the second one to send the signature. So this one, it sent the signature, server recognized that all the signatures were in broadcast immediately. The other one had to wait for a status update from the server.
The transaction also finds out if it doesn't receive everything in time.
Yep. It'll move to a failed state, and the client will automatically assume the mix has failed and doesn't have to worry because the transaction that it was creating hasn't been fully signed. Alright. That's our current work, our current proof of concept. Now let's move on to future work for improvement.
So there's a system that proposed on the same forum that CoinJoin was proposed that talked about a system called join market. So join market's interesting because it has a concept where there's two groups of people who would use this. There's people who have a lot of Bitcoin who are ready to join their coins at any given time, and then there's people who want to use the server. They have like a smaller amount of Bitcoin who just want to mix to use CoinJoin right then and right now and pay a transaction fee. So then the join market would just connect those two groups of people. The investors would just have their Bitcoins and be willing to be the other participants in CoinJoin, and then the people who wanted to mix their coins immediately would just pay to cover all the transaction fees. Then this system, that's one possible way to cover the transaction fees and the fees to the CoinJoin server and stuff.
So some other ideas that we had for transaction fees that still kept the centralized implementation were the first-time fee. So if the server would just see if there's an address submitting an input that's not from the output of another CoinJoin transaction, just block it until it pays a fee to the donation address. This would still preserve the multi-rounds, but then you'd have enough money in the donation address to actually supply you the fees for the entire server. The other idea that we had at the beginning, and this actually goes off of some other work that was done that Holden and Terry were working on with their coin lane. They found a Bitcoin lottery, and we found that the idea could possibly be used for fees, which involves two parallel transactions. One transaction is the main CoinJoin transaction, the large chunk, and that's used, but the difference is the output can only be redeemed by committing a random value X. And then have a parallel fee transaction that's very similar to a CoinJoin transaction, except the chunk size is smaller, and have a lottery based on the hashes that were committed for the first transaction be used with the second parallel transaction to determine whether the mixer will take the entire transaction or none of it. So can be used to generate that all or nothing randomized fees that was the fourth principle in Mixcoin. And I believe that's it. Yeah? Yes. So just briefly talk about it, we did start as a group of 4. It was me, Patrick, Holden, and Terry, Holden Lee and Terry Wang. We just did the initial planning stages together and then ended up submitting sort of 2 separate programs. Ours was CoinJoin and theirs was called CoinLang, which in the spirit of the script IDE was a way to program. It was a compiler for Bitcoin script where you could actually write the script in Haskell. A compiler would convert it to a circuit representation, and then that would be converted into the output of Bitcoin script. But there were easily plugins that could be added to output it to other languages like Litecoin script or Dogecoin script, any script that could be represented with a stack-based language. So we don't have their information right now.
Yeah, that's cool.
Yes, but all right, great.
Thank you guys. Questions?
Oh yeah, any